So I hope you're all ready for one more hour in this room. So let me have a show of hands first. Who of you knows what multiple instance learning is? We have one hand. Okay, a couple, but many of you don't, or maybe are too warm to move. So hopefully there's something to learn in the next lecture. This one will be a little bit shorter than the previous one. And again, no one dared to do it last time, but please, if you have questions, you can also ask during the lecture. Will be a better time to catch me than in the break right after. So far we have been looking at standard supervised learning. So we assume we have a training set with labeled samples. That's I think all the applications that you've seen today and in the past day. We think we have a training set with labeled samples. Samples can be, for instance, full images, if we're looking for imaging biomarkers, patients, or it can be voxels or patches if we're looking for disease localization, nodule detection, image segmentation. Samples are represented by a feature vector in feature space. I've drawn a few of them here. They have different labels. And then we train a classifier to learn the differences between classes. Now what if we have labels, but they're a little bit less specific than this? For instance, we only have collections of samples that are labeled, which could look like this. For instance, we have collections of samples, which we, in the multiple instance terminology, call bags. Samples we call instances. So we have bags of instances that have a label. For instance, all these samples we know do not have disease present, and all the red bags, they do have some disease present, but we don't know where it is. So bags could look like this. So I've drawn them like this. So of course, bags, they are just collections, any collections of samples that belong together. Could be, for instance, voxels from the same image. Bags, they could overlap in feature space, but typically every instance will belong to only one bag. So that's why I've drawn them in this case, in this way. So this setting is called multiple instance learning. And in medical image analysis, a bag will typically be an image, and our instances will be either voxels or regions of interest, patches or supervoxels or similar. So why is this useful? Well, it allows us to train on images for which we don't have local decisions, we don't have local labels, we don't have manual annotations. We only have an image information, but we can still make some local decisions. For instance, we know that there's pathology present in the image, but we don't know where it is. Compared to learning with localized labels, as you would do in voxel classification or ROI classification, of course the great advantage is that you don't need manual annotations. Manual annotations can be difficult to come by, for one, because it is very time consuming to make them. It's time consuming, it's expensive. Even more so, it may also be very difficult to make manual annotations. For instance, in the emphysema case that I showed before, we've actually tried to get our clinical collaborators to make of emphysema in the image, and they said they couldn't do it because they can see whether there's emphysema present. To some extent they can point it's here and it's not here, but they don't know where the boundary is. And in such cases, diffuse, the boundary may be very unclear. It can be more advantageous to have a label for the overall collection of voxels or patches, rather than really forced to have local labels that can be very uncertain. On the other hand, compared to learning with global labels, which would be the imaging biomarker learning approach, we have an image of a brain and we know whether this person is going to develop dementia or not. Compared to such global label, image label learning, where an image is one single instance, each bag has only one instance, so to say. Multiple instance learning may allow you to make more local decisions, which can be useful in cases where it's either not necessary to model the structure between all the different instances, the relations between all the instances in the image. You could imagine in the emphysema example case, it's not that important whether the patch you're looking at is where exactly in the lung it is and how it relates to other patches in the lung. A lung patch looks fairly similar whether you extract it from the top or the bottom of the lungs. It's not exactly the same, but interrelations are not that important. And then it can be too complicated to model the entire image as a whole, so it may be more beneficial to model regions. Often you will not have enough data to model the entire image as a whole in a good way. Here are some examples of applications that I so far have seen of multiple instance learning in medical imaging. One example is the example that you've seen before, COPD classification within lung CT. Typically, it's used quite often in histology images, where you have an histology slide. What is important are local patterns, which tell you whether this tissue is malignant or benign, but where exactly it is and how it relates to other benign spots or other normal tissue is not that important. Another example is in Alzheimer detection. This is from Dan Ruckert's group, so maybe you'll see something about it later. Where the instances are, in this case, patches in the image, the bags are images, and we know that some of these instances will be more important for the disease than others. So probably instances around the hippocampus will be more important than instances anywhere else in the brain. And if you don't have enough data to model all these relations, again, it may be good to just look at individual patches. Another problem, actually quite similar to the COPD example, is lung disease in X-ray images, where it can be, for clinical experts, or at least for me, it can be even much more difficult to delineate exactly where the disease starts and where it ends. So here are some typical applications. Now a little bit more on what is behind these techniques. Traditional assumptions for multiple instance learning are that there is a specific so-called concept. There is a concept instance, a concept feature vector that uniquely defines a positive bag. So that could be, for instance, the patches in an image that show whether a hippocampus has shrunk or has changed shape. Those are the concept patches that will be important in discriminating normal from disease. So this is the traditional assumption, and we'll see later that this may not be absolutely necessary. So there is a concept, and bags are negative only if all the instances in the bag are negative, and we call it positive. We call a collection positive as soon as there's one positive instance in the bag. So if you collect patches from an image, it actually makes sense. You can say this patient is healthy only if all the tissue within this patient is normal. And the patient has disease only if at least one of the patches in the images shows sign of disease. So these are the traditional assumptions for multiple instance learning. This can be relaxed, and it's probably a good way or a good idea in medical imaging. For instance, a negative bag may have some positives, but not too many. Positive bags should not have only one, but should have a certain percentage of positive instances. If we collect 1,000 patches from one patient and one of them shows a possible sign of disease, we may not want to classify this patient as, or this person as having disease. So the goals of multiple instance learning are then twofold, or at least the first goal is there. We want to classify unseen bags, unseen collections as good as possible. Often we also will want to classify the individual instances as good as possible, which is much more difficult because we don't have instance label, we don't have any specific information on them, so we need to make more assumptions there. It's more difficult, but it would allow us to possibly define disease regions without having local labels, and to possibly perform image segmentation without having any local training labels. So it's difficult, but would be very useful. There are three main types of multiple instance learning approaches that I'll discuss today. The first one is a naive approach. We propagate all the bag labels to the instance labels and then back. The second one is more related to the classical multiple instance learning approaches. There is this concept and we try to find out which part of the feature space defines our concept. And the third one is a direct bag classification, so direct classification of images as a collection of patches. So first the naive approach. So what we do is, well, we have bags, we have images with a lot of patches. Some of these images contain disease, others do not. For the images that do not contain disease, we say all the instances are negative. For the images that contain some disease, we say all the instances are positive. And it's quite likely that within those positive bags, there are some signs of disease, but the large majority of voxels or of regions of interest might be normal. But there will be some, at least one, there will be some instances that are positive, that are abnormal. But we assume for now to be able to train a classifier, we assume that all of them are positive. And then we apply this simple instance classifier. So we just train a regular classifier on those instances. Can be anything that we've seen so far. We apply this instance classifier and then combine the posterior probabilities that we get for each of the individual instances. For instance, just by averaging the posteriors, which could be good if you expect that there's diffuse disease. Most of the patterns in your disease class will show some sign of disease. You don't know which one, but most of them, the majority will show something. If you expect that that your disease is very focal, so only very few patches or regions of interest or voxels would show the disease, then something like a maximum probability fusion rule might be more appropriate. And of course you can play around with that. Maximum would be quite sensitive to noise, and you maybe want to use the 90th percentile instead. This approach, I call it a naive approach, it's because it's simple to do. If we know how to train a classifier, we can all apply it already. It often works quite well, especially on the bag level. Now the second approach was concept-based multiple instance learning. So these are the more traditional types of multiple instance learning. The first, when the problem or this way of looking at data was first proposed, the assumption was at least one sample should be positive for a bag to be called positive. So we have this specific concept that defines uniquely the positive bags, and we want to find out where in the feature space it is. So this concept should not overlap with any of the negative bags. We know that for sure because all the instances in the negative bags are negative. And it should contain from each positive bag at least one sample, one instance should be in this concept region. So yeah, this relies on the rather strict original interpretation of multiple instance learning. And in the example that I showed before, the concept that we would look for would be at least in this region, and it might be larger depending on additional assumptions. Now, how can you optimize that? I'll show just one example that is related to the concept-based approaches, which is me at multiple instance SVM. It's used quite often. It's an adaptation of standard SVM. So the aim is to find both the optimal labeling within the positive bag, where we don't know, so we assume the negative bag are all negative, that's the original assumption. Within the positive bag, we don't know. We don't know the labeling between positive and negative samples. So we want to find this optimal labeling, and we want to find the separating hyperplane, so that at least one of the instances in each positive bag is on the positive side of the decision boundary. All negative instances are on the negative side, and the margin between between the positive and negative labels for all the instances is maximized. Now this is something you can't just optimize directly. So what you would do is assume all the instances in a negative bag are negative, the other ones we don't know yet. You can't optimize this directly. A simple optimization heuristic is used for this. What we do is we first initialize by copying, again, propagating the bag labels to the instance labels. Then we train a standard support vector machine, could be linear, could be nonlinear, could be hard margin, could be soft margin. Then we iterate. We use the trained support vector machine to recompute labels in the positive bag. So the negative bag stays all negative. In the positive bag, we label them according to our current SVM classifier. Then, if you have positive bags that are labeled completely negative, you say, I want to label at least one sample, one instance positive in this bag, and you take the one that has the highest positive posterior, you force it to be positive, retrain your SVM, and then hopefully you'll come up with a classifier that both separates between imputed positive and negative labels in a positive bag and discriminates the bags. So this iterative approach was initially proposed for SVM. I haven't looked that much, but I've actually only seen it for SVM, but of course you can use it for any type of classifier, basically, to make a multiple instance learning approach. And the constraints can be relaxed. So the original version would say, if a positive bag, a bag that we know should be positive, but in my current SVM it's classified as fully negative, we want to label one instance as positive. You can go further and say we should have at least X% positive labels in a positive bag. We will allow some positive labels in the negative bags as well. So that would regularize the problem a little bit more. Now the third approach that I wanted to talk about is bag-based multiple instance learning. So we forget about this concept. We're not trying to search for this specific discriminatory part of the feature space. We're not trying to label instances. We only try to label the bags, and we model the bag as a whole. There are two approaches that I want to highlight, but I also should say these are in general approaches in classification. We have something that we want to classify. We either compute features from it and perform a regular classification, or we compute distances between samples and perform a dissimilarity-based, distance-based classification. So I'll start with the bag features. So we have this collection of instances that we want to describe as a whole, as good as possible. Of course, how you can best describe that depends on the type of data that you have and the problem that you try to solve. So you make a single feature vector for each bag that describes its constants, that describes all the individual feature vectors of the instances. And you could think of, for instance, just take the mean instance, or take the range of instances, the range of feature values you find within your bag, the minimum and maximum, the variances, the covariances. Typically, if there is indeed such a concept class, like tumor voxels in a patient who has cancer and other images where there's no cancer visible, if there is a specific concept class that can be found, then it's likely that this will be visible, at least in some features, as a minimum or maximum, that it is somewhere at the edges of the distribution. So in some cases this may work quite well. In many cases it will not work at all. So those are the simple, more aggregate measures. You may want to describe your feature distribution more accurately, and the way to do that would be by using a histogram. And then what you put in this histogram, what defines the bins of the histogram, will typically be determined by your data. It could be, for instance, done by clustering of all your training data, and then you find prototypes and you count the number of prototypes that are present. So prototypes of similar patterns, and you count the number of each prototype that is present in an image. That gives you a histogram, that gives you a feature vector. So that actually is similar to the bag of words approach that some of you may know from computer vision, which comes, I guess, from language analysis originally. So the idea is we can already get a good idea of what kind of document we're looking at just by counting which words are present in there and how often are they present. And you don't need all the relation between the words, how they are collected into sentences, to be able to do such a classification. Just the words and the frequency gives you a lot of important information. And it's a much easier distribution to work with. So similarly, you can do that in images. So this is a typical example of the bag of visual words approach. What we first do is we need to define our visual words, which are typical patches that we can find in different images. Our visual words in this case have been quite simple, but they are words that have been found in they are patches that have been found in different images, and the frequency of those patches will tell you a lot on what kind of object you're looking at. So that's that was a bag-based multiple instance learning approach. Remember, I wanted to discuss two bag-based multiple instance learning approaches. This was the one where you describe the bag as a whole as a feature vector. The other thing you can do is try to define distances between bags. So we want to define distances between collection of patches that tell you something about how similar they are. And typically we would expect our disease class, our patches, or our bags which have some disease in there, we would expect that one to be further away from a collection of only normal patches than another collection of only normal patches would be. So what we do is we define sensible distance measures somehow. We describe each bag in our training set by the distance to all the other training bags. So you see, you see it laid out in this figure. We describe each bag by the distances to all the other training bags, and then all those distances become our features, and from there we can perform, so then we just have a vector space, we can perform standard feature-based classification in that space. So each sample here is defined by its distances to all the samples in the training bag, including itself. And then you can compute any standard classifier like support vector machine or random forest, or another thing you could do is use a specific distance-based classifier that uses the distances directly, such as a k-nearest neighbor classifier. Then you don't need to build up this entire space. And then a new unseen bag, of course, you can also define by its distances to all the training bags and classify. Now here, our feature space, if we have a lot of bags, if we have a lot of training data, then our feature space can get quite large. There are approaches to reduce this feature space. You can think of manifold learning, embedding approaches. You can also just select prototypes either by clustering or by a random selection even of these prototypes. So it's important to look at the dimensionality of your data, the number of samples that you have, and whether, where are you on the learning curve? Do you have a dimensionality problem or not? Can you handle the complexity of your current model? A popular approach for multiple instance learning is also based on this dissimilarity concept, but slightly different than the general approach that I showed before. It's called MILES, multiple instance learning via embedded instance selection. And what it does is it computes distances to all the instances. So your bag is defined not just by distances to all the training bags, but by distances to all the training instances. So that quite quickly explodes. You get a very high dimensional feature space. How they cope with that in the original paper is to use a one-norm SVM, which then essentially selects a few instances. So you do a sparse classification. You select instances that are important for the bag level classification. So this is a bit similar to the concept-based approach, but it's more general. So the instances that you select, they could be from either positive or negative bags. They are important for the bag level accuracy. They're not necessarily related to a specific only positive concept. And there could also be multiple distinct types. So now for some results. The case study. As you probably have suspected already, the example that I showed in the previous lecture, COPD classification from CT, it is based on a multiple instance learning approach. So the typical approach, and that has also been used in emphysema characterization, is that you would take a few samples, you would have an expert indicate which patch contains emphysema and which patch does not contain emphysema. As I already told you, our experts would not do that. So we had to do something else, and also we wanted to see how far you can push these methods without having any additional local information. So the standard approach would be have patch labels, compute a lot of texture filters, train a classifier based on that. What we did instead was we select completely randomly samples in the image that are small three-dimensional patches. We used the naive approach, so we propagate the disease label to the instance labels, compute texture filters. What we did here was again, so it was a Gaussian multi-scale feature bank with only rotational invariant features. We looked at the feature distributions, and then we defined a distance based on histogram distances for the different filter distributions. And the histogram distance we used here was the earth mover's distance, but you could use other distances there, of course, as well. But yeah, in general, earth mover's distance is a good one to use with histograms. And then we used, so we have a distance measure, then we used the k nearest neighbor classifier as our instance classification. And then that gives us the result that I showed before. Texture measures perform better than conventional density measures in detection of COPD. Now that was just the naive approach, which actually works quite well in this case. We've looked a little bit further and looked at whether we could define good bag dissimilarities. So we did use histogram dissimilarities, but they were only on the instance level so far. So what would be good bag dissimilarity measures? So we take some examples from each bag, and we want to define a distance measure based on the instances. So a good baseline, we didn't expect it to perform well, but a good baseline would be the Hausdorff distance. You compute for each instance its closest neighbor in the other bag, and then you take the maximum of those. But it's based on just one pair of instances, so it might be a little bit sensitive to noise. Another one that we did not expect to perform well, but actually did perform well in some cases, is just computing the sum or the mean over all the distances, all the possible pairs in the two bags. And then what does seem more sensible, if you assume that you're looking at disease patches and normal patches, is to try to pair disease with disease and normal with normal. So what you can do is compute for each sample the minimum distance to an instance in the other bag, and sum that over all the instances. And then it's asymmetric, so you typically do it both ways. Another one that I liked a lot is a linear assignment. What we do here, it only works well if we have the same number of instances in both images, which we can do here because they're just random samples. We want to pair disease and normal as good as possible. So what we do is we want to find a unique pairing that has the overall minimum distance, which has the effect that images will only be similar if they have an equal number of equally diseased patches, which seemed to me like the best approach if you want to classify COPD. We know that there are really patches where COPD is present. We know that there are definitely patches where the doctors don't find any signs of COPD, even in the normal case, or even in the COPD cases, and definitely in our data, which is quite early disease stage. And this way you can really find the right type of distances. So we found that in some cases the dissimilarity approach is better than the naive approach. So the naive approach is here. You see it's all areas under the ROC curve. So here are the original density measures, and this is similar to what I showed before. The texture measures in the naive multiple instance learning approach perform quite a lot better. Now, if we use, so here are the different distances that we've tried. So the Hausdorff distance doesn't perform very well. Some distance actually performs well in some cases. And the minimum sum and linear assignment distances perform quite well, but still it also depends a lot on what kind of classifier is used. So if you use the distances directly, that actually works quite well. If we use K and N in the dissimilarity space, it actually does not work that well in many cases. But if you then in the dissimilarity space, which can be quite high dimensional if you just train a linear classifier there, this was a linear SVM, then it performs quite well and better than the naive approach. But this is very, very data dependent. We did a little bit further comparison of different approaches and also with some standard popular benchmark. So we also tried mouse on this data. It didn't work at all. 50% area under the curve, and it was a balanced training set, so this is random performance. Here are the naive approaches, but with different classifiers, and they do work quite well. These are the dissimilarity-based approaches, so that's similar to what I showed you before. And what I should also point out here, that here our winner is actually just computing the mean feature vector in the bag and then performing a classifier. So I don't remember whether it was a linear or RBF classifier, but this actually shows that we thought it was a multiple instance learning problem. We thought it was a good idea to do a local analysis. In the data that we have, I think the disease is so diffuse that it actually would have been equally good to just compute the overall histogram and not look at individual instances. I must say that because we're looking at a lung cancer screening trial, and these patients, so due to the trial, they have been diagnosed as COPD. The vast majority has mild COPD, but they didn't know that before entering the trial. And actually you have to be quite healthy, you have to be quite fit to enter such a trial, because you need to be fit enough to go into surgery if they find something. So they had, so one of the requirements was that you needed to be able to walk 3 flights of stairs without stopping, and otherwise you can't enter the trial. So these were all people with quite early stage COPD. And in those images, in some cases you do see these these localized signs of the disease, but I think it becomes worse in the more severe stages. So I think it can be useful to do multiple instance learning on such data, but we haven't been able to show it on our data set. So, which multiple instance classifier is best? Well, as with any classifier, with any classification or machine learning approach, this is very data dependent. It depends on the problem that you have, it depends on the complexity of the data, the amount of training data that you have, but also on whether you expect that there is this specific concept, or perhaps are there perhaps multiple concept regions that really uniquely define positive and negative, or do you expect that it's not that clear, that you can't, that there may be differences, but you don't really expect this to be localized in the feature space that you have. So what you see here is the more traditional idea of multiple instance learning. We do have a positive and a negative class that are, on the instance level, they are quite similar, but there is this region where they are different. And that's what we can find using multiple instance learning, or especially with the more traditional approaches. And in some cases, your data may look more like this, which I think is the case in our lung classification problem. So in that case, it can be better to not go for the concept-based approaches, but more for instance, a naive approach or direct bag dissimilarity approach. So one more thing to highlight is that, of course, if we have good image level, bag level performance, even if we use a classifier that does also classify instances, it doesn't mean necessarily that the instance classifications that we get out are good. So here you see an example again of the COPD texture classification case. So we had 50 random samples in each bag, and this, what you see here is one bag that had been classified 10 times with a slight perturbation of the training set. So 80% of the training set remained the same and 20% was varied. And there was a correct bag classification in all cases. So the bag is positive, it should contain positive samples. But would you expect, so if the instance classification would be good, you would expect some samples to be never classified as positive and some samples to be always classified as positive. And that's clearly not the case here. Now, of course, this is a problem that may not in its current state be really a multiple instance learning problem. The disease signs are very diffuse and that will have caused some of this. But in general, you can't assume your instance level classification to be stable and accurate just based on a good bag level classification. So I had a part that I thought I would probably skip. I think I'll skip it. So then we have a little bit more time for questions. Yeah. So this multiple instance learning image level labels allows, in principle, it could be very useful. It allows large-scale biomarker discovery in clinical databases. We don't need any manual annotations. All we need is a label describing disease. The current approaches that I showed, they require this label to be quite standardized. Well, in our case, we actually had just disease or no disease. And you can think of a little bit more advanced labels, maybe also giving the disease severity, but they should be standardized, they should be interpretable in the same way in different clinical databases. And that, of course, would be a problem as well. So I think where this should go eventually is to learn from hospital databases and hopefully to learn from the much more rich information that is present in radiology reports. So this will go both ways. Radiology reports will become more and more standardized so that it's easier for us to train on them, but also we can make more effort to use these reports in a better way and then have not just information on disease status, but in some cases we would also have information on type of pattern and a rough location of where the radiologist sees this disease, which could help a lot in training better classifiers on weak labels. So I've only talked about image level labels, which is, well, a very important source of weak labels. You could think of other, so I wanted to briefly touch upon other examples of weak labels in case you had expected something completely different from this lecture. People have been working with rough segmentations, for instance, just a bounding box around a pathology or around an organ that you want to segment. Yeah, not a complete image, but just a bounding box. But there, a similar multiple instance learning approach could be helpful. You could think of performing segmentation by crowdsourcing, which means that you will get some results that are quite good. Some segmentation tasks can easily be done by non-experts. It's just a lot of work, but if you can see the boundaries in the image, also non-experts can do it. But if you do crowdsourcing, then you will also get a lot of rubbish results, and you need to deal with that somehow. In that case, I think finding a way to determine the uncertainty or the reliability of your segmentations and using a weight and then a weighted classifier could be the way to go. Another example could be if you want to learn from incomplete segmentations. And this is something that I mentioned also in the previous lecture, so in the domain adaptation approach. So there actually you can use a density-based weighting. Here's an example, another example from the lungs that I wanted to show, which shows you that actually you can get quite good results with not so good labels. So the task here was to perform airway segmentation. And on the left you see Yeah, the current more standard approaches, which are just based on intensity and intensity region growing. So they look like this, and well, maybe I should show you one of the slides that I skipped. So this is what airways look like. On the left you see a plastic cast of airways, which are in white, and vessels in blue and red. So that is what airways should look like. Of course, in CT you find fewer of them, but what we found here in the intensity region growing is not enough. Now, if we use this one for training, and then train a voxel-based classifier, and then, so if all our examples did not find any of the smaller branches, then we would be lost. But the nice thing is that in some cases we do actually find, we are lucky and we find a branch that goes quite deep into the lung and becomes smaller and smaller. Now, if we know about those examples and we put in some additional information that those examples are important and we weigh them higher than the examples that are quite trivial here, then you can get a result that is as good as this. So based on these rather poor segmentations, you can get a segmentation just by simple voxel classification that is up there with the state of the art at the moment. So a little bit of discussion to end. The best multiple instance learning approach depends on the goal and the data distribution. Well, I think I've mentioned that enough times by now. Do we need to define the region of interest? So in our case, I probably didn't mention it very explicitly, but what we did was first segment the lungs and then make sure that we sample patches only within the lungs. Is that absolutely necessary? I think not. If we have enough training data, we should be able to eventually to learn from the entire image directly. At the moment, if we so we are not easily in the case where you have too much or enough training samples. You can afford to not do simple hacks to make your problem a little bit easier. So I have seen a paper where they they did a very similar texture classification approach, and they sampled patches randomly over the entire image, and they found actually a lot of patches that the classifier thought were important, that were outside the lungs and even outside the body. And so that they said, well, we know that there are different phenotypes of COPD, and actually fat people, they get a different phenotype than thin people, so it makes a lot of sense. I doubt whether that's really the case or whether it's just an overtrained pattern recognition system. So if you can easily define a region of interest that you know is important and you are quite confident that nothing outside this region should be taken into account, then you should definitely do it. All the examples that I showed, they completely discard any spatial relation between the instances, which is typically not what we do within medical image analysis, and maybe we're simplifying the problem too much. I think in the lung texture case it's pretty safe, but still we do know that just based on gravity, how you lie in the CT scanner, and how the airways and the vessels are structured, the patches will look a little bit different dependent on where you are in the image. So it may be better to include spatial information. You can try to model the entire image. You can also try to go somewhere in between and use some spatial correlations between instances in your multiple instance learning approach. So you could think of graph kernel approaches, for instance, as one example of those cases. And then an open question also is still how to combine weak and strong labels. So what I showed is how you can learn from weak labels if that's the only thing you have. But if you happen to have a few strong labels, a few local labels, it will be much better to include them. And of course you can easily include them just by labeling them according to the label that they should have, and in the different iterative approaches that we saw keep those labels fixed, you probably need to give them a higher weight, but how to do that in a very nice way, that no one has looked at that yet, I think. That was all. Thank you.